Electrical cardiometry, Wikipedia audio. Electrical cardiometry is a method based on the model of electrical velocimetry, and non-invasively measures stroke volume, cardiac output, and other hemodynamic parameters through the use of 4 surface ECG electrodes. Electrical cardiometry is a method trademarked by Cardiotronic, Inc., and is US FDA approved for use on adults, children, and neonates. The measured bioimpedance over time can be expressed as the superposition of 3 components, where Z0 is the quasi-static portion of the electrical impedance, delta ZR are the changes of impedance due to the respiratory cycle, and delta ZC are the changes of impedance due to the cardiac cycle. Delta ZR is considered an artifact akin to the estimation of stroke volume and is therefore suppressed. Exclusion of derived volumetric data may diminish the overall product. Overview. The timely measurement of delta ZC reveals a waveform with shape similar to an arterial pressure waveform. The calculated first-time derivative of dz is the d, z, t, d, t waveform, which contains landmarks that allow determination of left ventricular ejection time and peak aortic blood acceleration. The peak aortic blood acceleration occurs at the steepest slope of the dz waveform, and at the peak of the d, z, t, d, t waveform. Electrical velocimetry is the model which electrical cardiometry is based. EV is based on the fact that the conductivity of the blood in the aorta changes during the cardiac cycle. EV was developed by Dr. Bernstein and Dr. Osipka in 2001, as a new model for interpreting the bioimpedance signals of the thorax. Prior to opening of the aortic valve, the red blood cells assume a random orientation. When the electric current is applied from the outer electrodes, the current must circumference these red blood cells, therefore resulting in a higher voltage measurement, and thus, a lower conductivity. Shortly after aortic valve opening, the pulsatile blood flow forces the red blood cells to align in parallel with the blood flow. When the electric current is then applied, it is able to easily pass the red blood cells in the aorta, resulting in a lower voltage, and thus, a higher conductivity. The change from random orientation to alignment of red blood cells upon opening of aortic valve generates a characteristic steep increase of conductivity or dz beat to beat. The model considers the peak amplitude of d, z, t, d, t, divided by the base impedance Z0 as an index for peak aortic acceleration, and as an index of contractility of the heart, or icon. The general equation for estimating stroke volume by means of thoracic electrical bioimpedance calculates the product of a patient constant Cp, the mean blood velocity index, V, Ft. S, V, T, E, B, equals, Cp, V, F, T, F, T, equals C/Ft. The model of electrical velocimetry derives the mean blood velocity index, V, Ft from the measured index for peak aortic acceleration icon. The higher the mean blood velocity during flow time, the more SV the left ventricle ejects. The volume of electrically participating tissue is used as the patient constant. The VEPT is derived primarily from the body mass. Impedance cardiography is a method of non-invasively monitoring hemodynamics, through the use of 4 dual sensors placed on the neck and chest. Both impedance cardiography and electrical cardiometry derive SV and CO from measurements of TEB, but the underlying model is what differs. The impedance cardiography model contributes the rapid change of bioimpedance which occurs shortly after aortic valve opening to the expansion of the compliant ascending aorta, assuming that more blood volume temporarily stored in the ascending aorta contributes to a decrease in bioimpedance. The underlying model never proved accurate in patients with small cardiac outputs, hence it was never US FDA approved for use in children or neonates. The electrical and impedance signals are processed, and then utilized to measure and calculate hemodynamic parameters such as cardiac output, stroke volume, systemic vascular resistance, thoracic fluid index (ICON), and systolic time ratio. Theory: Electrical velocimetry. Comparisons. Impedance cardiography. Parameters.